Okay. Hello, everyone. Thank you for coming to the summit, and thank you for coming to my talk. I'll be showcasing our integration of Hugging Face with Ray AI. So before we begin, just quickly about myself. So who am I? I'm Antoni. I'm a software engineer at Anyscale. I've been on the libraries team for a little over a year now. The libraries team is working mostly on Ray AI Runtime now, which means train, tune, all the different ecosystem integrations. And in my spare time, I'm maintaining several open source projects. So you probably heard about Anyscale, but just to briefly set some context here. So we at Anyscale are original creators of Ray, a unified framework for scalable computing. And what we do is we want to create a scalable compute for AI and Python. And we do it because scaling is hard, and we want to make it as easy, as simple for everyone. And we hope that this Hugging Face integration is going to be an example of that. So an agenda for today's talk is that I'm going to quickly introduce Hugging Face as a library. I will showcase the state of distributed training and why it is a necessity. Briefly show how Ray AI can superpower Hugging Face to easily run distributed training on multiple GPUs on a cluster. Do a deep dive into the internals and API of our Ray AI Runtime Hugging Face trainer, and we'll end with a quick demo. So yeah, the state of machine learning, as we all know, is that at this point, deep learning is state of the art. And we have been seeing some really impressive foundational models. So for example, GPT-3. So those are very large models with billions of parameters that can do some quite incredible things. But not only models are getting bigger, the data is also growing bigger and bigger, which means we need more memory, we need more compute. And ML is pervasive across all domains. So you can see a use for machine learning in finance, in biochemistry, in science, and there are multiple uses for it. So Hugging Face Transformers is a library for easy use of state-of-the-art machine learning. It is simple, robust, and powerful. It is a library for Python which provides an opinionated, high-level API wrapping around libraries such as PyTorch, TensorFlow, and JAX. It is mostly focused on natural language processing, though there has been work on computer vision, audio processing, and other modules such as that. And one main selling point, in my opinion, is that it provides access to multiple state-of-the-art pre-trained models. You can very easily obtain, for example, GPT, BERT, and multiple other models, and you can use them in whatever way you want. And it has a huge community and a huge social focus. The Hugging Face Hub, which is a service Hugging Face provides, allows access to multiple models, data sets, and you can easily download and upload your own. So how does Hugging Face make machine learning easier? So first of all, it abstracts many complexities of deep learning. With just a few lines of code, you can use a pre-trained model for inference, you can fine-tune it, you can easily get and upload models. It has great developer velocity thanks to that. And it provides the Hugging Face Hub, which, as I mentioned, is a repository of models and data sets where you can obtain and share your own work. So here's an example of a typical Hugging Face workflow. So we are using the Hugging Face datasets library to load a dataset from Hugging Face Hub. We are splitting it into train and evaluation dataset. We'll be doing sequence classification here, so we are obtaining the BERT model from the hub. We specify the training arguments and then initialize the Hugging Face trainer, and we just train the trainer. So as you can see, in just a couple of lines of code, we can quickly obtain and fine-tune a model for our use case. However, all those state-of-the-art models, they need a lot of compute. So as we can see, the amount of parameters and the amount of memory required for models has been growing in an exponential fashion. And the fact of the matter is that Moore's law and advances in hardware have not been able to keep up with that. So as Jon mentioned, there is no way but to go distributed. We simply cannot do the training of such large models on a single node. So for example, GPT-3, if we were to train it on a single V100 instance, that would take over 350 years. So even if you have a beefy instance with 8 GPUs, that is still going to take 40 years to train. So there is no way but to go distributed. Yeah. OK, so we go distributed. But now we can see new problems. So first of all, developer velocity drops down dramatically. We have to make sure that we know how to set up our model on multiple nodes, that we can deal with fault tolerance, that we can make sure that we are taking care of all the infrastructure problems. So for example, AWS, this is all knowledge that wasn't necessary before. Those are all skills that weren't necessary before when we were developing on a single node. But now they are bringing our developer velocity down. We have to start to learn how to manage complex infrastructure. So we need to, for example, make sure that we know how to set up a on-premise cluster if you want to go for that, or how to deal with AWS, GCP, what are the different node types. And in the end, even if we get our training to a distributed state where we can scale it up, it doesn't end there. We have to make sure that the entire machine learning pipeline can be scaled up. We don't want to have any bottlenecks, and we want to make sure that we are not only able to train in a scalable fashion, but that we can make sure that our data ingest, hyperparameter tuning, and serving can also be scaled up. So what is the solution to those problems? So in our opinion, the solution is here, Ray AI, which is a scalable, unified toolkit for both data scientists and software engineers. And Ray AI provides a flexible Pythonic framework for each step of the ML workflow. So we cover all the steps from data ingest through data preprocessing with Ray Data, training with Ray Train, tuning with Ray Tune, and then you can easily do inference and serving at scale, all the while staying entirely within the Python ecosystem and being able to use all your favorite libraries, including Hugging Face, while being distributed with Ray. So here's an example of how the Ray AI ecosystem works. So as you can see, we built on top of Ray Core. The AI Runtime is built on top of Ray Core and provides advanced functionality and integrations with all the popular machine learning libraries. And we provide APIs that allow users to write their own integration with whatever library or use case they may be facing. So why are we using Ray in the first place? So first of all, Ray provides an efficient data layer and distributed object store, meaning you don't have to worry about how to get data from one node to another. It provides a fully Python-based API, so you do not have to leave Python even for a moment. And it provides robust scheduling and resource management, taking away the complexities of managing infrastructure. So in short, Ray provides the compute strata, infrastructure management, and all the solutions for the challenges of distributed computing. So now we want to focus on how we combine Hugging Face and Ray and what sort of benefits we can gain from that. So let me start with a quick showcase of our Ray AI Runtime Hugging Face trainer. So trainer is a concept in Ray AI Runtime which wraps around different libraries and allows you to do training at scale. So first of all, we use the existing Hugging Face code in a function. So we are not reinventing the wheel here. We take your existing Hugging Face code, or you can take code from a Hugging Face example. All you need to do is you have to put it in a function, and you have to return the trainer from Hugging Face. Then we need to provide the scaling config and other Ray AI Runtime configs as needed. So scaling config determines on how many machines will be distributing our training and whether we are using GPUs or not. So in this example, we'll be using 3 GPUs. And once we have a Ray cluster, then all the scheduling will be taken care of by Ray. We define our Hugging Face trainer using Ray datasets for data ingest and data preprocessing if needed. So Ray datasets take care of transferring the data between nodes and allowing you to, for example, use datasets that are bigger than the memory of one node or even bigger than the memory of an entire cluster. And at the end, we simply call fit on our trainer, and we obtain a results object which we can inspect, get the best checkpoint from, and carry on over to next step of our machine learning pipeline. So how is Ray AI Hugging Face trainer implemented? So in essence, it uses distributed data parallel training on an array cluster, and it takes advantage of the PyTorch DDP training and the fact that Hugging Face is a wrapper around PyTorch and other libraries, but we are focusing on PyTorch here. It allows you to run any user-defined Hugging Face code without any changes. So you do not have to make any specific changes to allow for distributed training. You can take the existing code and make sure that you can run it with Ray AI trainer. It automatically converts the Ray datasets to the format expected by Hugging Face. So this is also another thing that is abstracted. And it provides built-in logging and monitoring, for example, with MLflow, TensorBoard, and other libraries. So we parallelize the training using PyTorch DDP. So what that means is that we have several workers scheduled on array clusters. So for example, each worker may be using one GPU or multiple CPUs. Each of the workers gets a shard of the data, and they each train the same model, and the gradients are synchronized during iterations. The Ray AI trainer abstracts away the infrastructure, so you do not have to worry about setting up those workers yourself. They are all set up automatically. And we support both CPU and GPU workers with TPU support incoming. So for data ingest, we are using Ray datasets as a common data format. This is consistent with the rest of Ray AI. This allows us to easily read from disk, cloud, or other formats. So for example, if you have a pandas data frame, you can easily convert it into a Ray dataset. Ray datasets are fully distributed, and they can even handle data that is too big to fit on any single node or even on an entire cluster. And they can also run transformations in parallel, speeding up your data preprocessing. So for data preprocessing, we have a concept of preprocessors, which we provide several out-of-box examples for. You can also write your own user-defined functions for map apply, and they are automatically applied during training and inference if you pass them as an argument to the Ray AI trainer. And here you can see an example of a tokenizing function that is passed to a Ray AI batch mapper and used as an argument in the Hugging Face trainer. For logging and monitoring, we have multiple callbacks. You can use MLflow, weights and biases, TensorBoard, and other such libraries. And you can even write your own callbacks with a simple API that we provide. And you can also inspect the result object after training, which contains the metrics, the best model, and so on. So checkpointing for Ray AI is fully automatic and can be configured to, for example, only keep the best checkpoint. You can resume training from the checkpoint object, and this system allows for spot instance usage. If a node goes down, the Ray autoscaler will automatically bring it back down, and the training will be resumed from the latest checkpoint automatically. And checkpoints can also be passed to predictors and to Ray serve for easy inference and serving. So here is the typical Hugging Face training workflow as I showcased before. So now that we want to distribute it with Ray AI, those are all the changes that we have made. So first, we need to put our model and trainer initialization logic inside a function. We call it trainer init per worker. We instantiate the Ray AI Hugging Face trainer, and we simply call fit and obtain the results object. So just to summarize, we are using Ray datasets for ingest, and we are using existing Hugging Face code, and we can easily integrate with rest of Ray AI Runtime. So for example, if you want to run a hyperparameter optimization search, we can simply use the Ray AI tuner just by passing the Hugging Face trainer into it, and it will run multiple trials in a distributed fashion. And for inference and serving, we pass the checkpoint object into a Hugging Face predictor, which uses Hugging Face pipelines under the hood. That means that you will get the same outputs as with non-distributed Hugging Face, but they will be returned in array dataset format so that they can be used on array cluster. So here is an example of calling the predictor, using the batch predictor so that the prediction is parallelized as well. Okay, so I have prepared a quick demo. So if we could quickly switch here. Okay. So this is based on a Hugging Face example notebook, and it has been simply distributed with Ray AI. We'll be doing a fine-tuning of a model on text classification task, and we'll be also hyperparameter tuning it and doing some predictions. So first, let me connect to a Ray cluster. This is all running in an AnyScale workspace. So let's just check what sort of resources we have. So we have 16 GPUs. So we will run the training on 4 workers, each with 1 GPU. So in the interest of time, let me just quickly skip over the initialization here. We're just defining the glue task that we'll be working on. We are obtaining the tokenizer and the model from the Hugging Face hub. We are using Ray data from Hugging Face to easily convert the Hugging Face dataset to Ray datasets. I'm just limiting it here for brevity. We are defining our preprocess function, so what it will do, it will use the Hugging Face tokenizer to tokenize the data before passing it to the trainer, and we are saving it as a batch mapper preprocessor. So here is our trainer init per worker function. So all we do is we are obtaining the tokenizer, the model, we are defining the Hugging Face training arguments, we are defining our custom compute metric, initialize the trainer, and we return it. So this will be run on every Ray worker, and the training will proceed in a distributed data parallel fashion. So here is our Ray AI trainer. We pass the function that we have just defined into it. We specify the scaling config with the number of workers, the datasets that we'll be using, the run config. So we are using the MLflow logger callback for logging, and we only want to keep the best checkpoint using the evaluation loss as a metric. And we are also passing our preprocessor, which will be tokenizing the data. So all we have to do now is call trainer.fit, and we can see that here is the output for it. So every iteration of the training, every epoch, you will receive a report from the trainer with all the different metrics. We are also working on steps support, so you'll be able to not only report every epoch, but every, for example, 500 steps. So let's give it a moment to run. So while it's doing its thing, so we can see that it's running training, running evaluation. We can see that it's starting to report the iterations, and the widget is also getting updated. So I've only set it to 2 epochs. So the training has completed, and we get the result object back. And we can see the last reported metric. We can see the checkpoint, which is saved in a local path, and we can easily convert that to, for example, an S3 path or an in-memory object. So now that we want to tune hyperparameters, all we have to do is pass our trainer into a Ray AI tuner. We define the parameter space, so we'll be optimizing learning rate using grid search. We define the metric that we want to use, whether we want to minimize or maximize. And we are also using an ASHA scheduler here. So Ray AI provides several advanced searchers and schedulers that can speed up your training. So the ASHA scheduler will aggressively early stop underperforming trials. And this can also be combined with a resource allocating scheduler, which allows you to reallocate the resources from stopped trials into running trials, maintaining full resource utilization, and thus letting you finish your hyperparameter optimization faster. So we are just letting it run here. So the widget is updating. So we have 4 trials running in parallel. So each of those 4 trials is also running in a distributed fashion on 4 GPUs for a total of 16 GPUs. And we can see that we are obtaining results back already. So let's give it a moment to run. So while it's doing its thing, let me just quickly showcase the next step. So afterwards, we can obtain a data frame of all the tuning results. And we can also get the best result by evaluation loss or any other metric we may specify. So let's quickly check how the optimization is progressing. Yeah, so we can see the ASHA scheduler is terminating trials that are underperforming, and we are only left with 1 running trial, which is the most promising. So I've set it to run for 4 epochs, and we are about to be done with the tuning. So here is the data frame of all the evaluation results. And of course, you can use different logging callbacks with it. You can use TensorBoard to monitor your progress, MLflow, weights and biases, and any other library you may think of. So we have obtained the best result object. And now we can predict on our test data. So we are instantiating the batch predictor. We are using the best result to obtain the checkpoint. We'll be using the Hugging Face predictor as our predictor class. The task is text classification, and we'll be running the prediction on GPUs. So as you can see, Ray automatically schedules actors to carry out the prediction in a distributed manner, and we can see that this is those are the labels that we have obtained on test data. And we can, of course, later we can save that prediction from a Ray dataset to a Parquet file, for example, or we can do online inference with RayServe. And this concludes the demo. Yep, so happy to take any questions, and thank you all for listening.
Hey, I'm Tyler. I was just wondering how this works with like Hugging Face spaces. So if I'm trying to create like a Gradio or a Streamlit app like on top of this, is it just kind of the same typical workloads that I normally do with spaces, or is there any difference that I have to worry about?
So we do not support spaces just yet, but this is one of the features that we want to be evaluating for support. Right now, the main focus is fine-tuning and prediction at scale.
Hi there, my name is Prashant. When you showed the part where you connected to the AnyScale cluster, how easy is it to change that methodology to connect to, let's say, an external cloud like AWS or any other?
Yeah. So it is quite easy. So we are using an AnyScale cluster here, but you can also do the same thing on an OSS Ray cluster using the Ray Cluster Launcher. You can use AWS, GCP, Alibaba, or on an on-premise cluster. And once you have a Ray cluster, like you can run pretty much any Ray Air workflow on it.
Hi. What do you think this would look like if you used Ray for the data parallelism instead of using Hugging Face and PyTorch DDP under the hood? Like, what level of surgery would it require to do that?
So just so I understand correctly, so you just want to use like pure Ray for everything, for the training as well? Yeah. Well, so obviously you can create your own training library using our libraries and Ray core. I know that somebody was working on a fully Raytonic decision tree as a toy example. But in general, what we are trying to do with Ray AI is that we are trying to wrap around popular libraries and handle all the boring infrastructure and orchestration stuff so you can focus on what's important in your machine learning lifecycle.
Thanks for the demo. So this looks really cool. Am I correct in understanding that the main difference between the RayTrain API as it exists today and then the RayTrain API from Air is that from Air it's more composable, so you can like pass it into tuner and then anything else that comes after, or are there any other like key differences that you wanted to highlight as well?
Yeah, so with Ray AI, we are trying to provide a unified API for all of our libraries. So as you have said, yes, composability is one of the new advantages of the new API. But in general, we have been trying to make it simpler, hide away some of the complexity, and make it more familiar. So as you might have noticed, for example, we are using some of the scikit-learn terminology, such as fitting and transforming. So we are not 100% following scikit-learn, but we have obviously used that as an inspiration, and we hope that it will allow people to just start their journey with Ray quicker than it is currently with the old APIs that weren't that great, let's be honest.
So I want to ask a little bit about the fault tolerance. So I want to ask, where does the checkpoint get stored?
Yeah.
If for example, the hand node crash, were we still able to kind of resume the proper checkpoint?
Yeah. So by default, what we do is we save the checkpoints on a head node. So the checkpoints are transferred from worker nodes to the head node. But you can very easily set up checkpointing on S3, on NFS, and on multiple different cloud storages. So for persistence, it's just basically using a Ray AI run config, and you can do checkpoint config there and specify where you want your checkpoints to be saved.
Hi, probably follow-up question about the fault tolerance. So does the elastic training on a schedule for like supporting in the future? If so, what kind of elastic training you're going to support? Yeah.
So yes, elastic training is something that we would like to add. It's hard for me to say right now what kind of elastic training we'll have, but definitely I can see like warm restarting, for example. So in one of our existing libraries, XGBoost Ray, so for example, it has full elastic training, and this is something that we would like to add to our other trainers, but yeah, so far it is still in the planning stage.
Hi, I'm Nikunj. You mentioned that we can visualize the results on TensorBoard,
yes.
Weights and biases, MLflow, etc. Is there any tight integration with some of these libraries, or it's on the user on what experiment tracking library they want to use?
Yeah, so we provide several built-in callbacks for the popular libraries, but you can very easily add your own callbacks. So if you are using some library that is not built, for which an integration is not built into Ray AI, you can very easily add that integration and use whatever experiment tracking library you want.
Can you talk briefly about how different kind of training parallelism are supported?
Yeah. So we are focusing on data parallelism right now. So this is the main paradigm that we want to support really well. But we are also starting to support model parallelism with Alpa. This is not yet released, but we are hoping it will get merged into master soon, and there will be a Ray AI Alpa trainer for easy model parallelism. Okay, thank you all. And yeah, if you have any more questions, please let me know. Unfortunately, the slide isn't displayed, but yeah, you can find me on LinkedIn, and you can find me on the speakers portal on the app. So yeah, happy to connect and chat if you are interested in more. Thank you all.